Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is electrically excited synchronous motors. Our objective is to discuss the construction and theory of operation of electrically excited synchronous motors, as well as examine their mechanical and electrical properties while in operation. We'll additionally examine how field strength influences pull-out torque and performance at various load conditions. This lecture operates under the presumption the viewer has watched the Motors and Generators playlist in its intended sequence and comes fully armed with an understanding of the motor family tree, electromagnetic interaction, the stator rotating magnetic field, and rotating mechanical power. Additionally, this lecture presumes the viewer has an intimate level of familiarity with the mechanical and electrical properties of three-phase AC squirrel cage induction motors. If you haven't watched these lectures yet, or only dimly recall their contents, please bring yourself up to speed and return when you are so qualified. In the aforementioned lectures, we acquainted ourselves with a larger motor family tree, various properties common to all motors, and then, like some heavily caffeinated squirrel, climbed high into the squirrel cage induction motor branch of the motor family tree and rattled every leaf, shook every twig, knocked out every bird nest, and gnawed every acorn until nothing was left. Today, we're going to climb back down and back up again to the electrically excited synchronous motor branch and do the exact same thing. Before we do so, let's pause at the split between three-phase AC induction motors and three-phase AC synchronous motors and discuss some commonalities for these two important styles of three-phase AC motors. Both synchronous and induction three-phase AC motors are characterized by a rotating magnetic field on the stator. The speed of the rotating stator magnetic field is known as the synchronous speed and is directly proportional to the excitation frequency and inversely proportional to the number of pole pairs per phase. Additionally, the direction of the rotating stator magnetic field can be reversed simply by interchanging any two stator leads inside a three-phase AC system. Lastly, one can determine rotating mechanical power in units watts as a product of torque in Newton meters times rotational speed in units of RPM divided by the constant 9.55. These properties remain true for all three-phase AC motors, synchronous and induction. The division between the synchronous and induction split in the three-phase AC motor branch is based on performance with respect to the synchronous speed. As the name implies, the rotor speed of a synchronous motor, the topic of today's discussion, matches, follows, or is otherwise synchronized or locked in step with that of the stator rotating magnetic field, whereas the rotor speed of an induction motor is not. The rotor of an induction motor must necessarily slightly lag behind the synchronous speed for them to function at all, even in the no-load condition. It is for this reason induction motors are sometimes called asynchronous motors, meaning not synchronized. I say again, the rotor of a synchronous motor is synchronized with the stator rotating magnetic field, whereas the rotor of an induction motor is not. The rotor of an induction motor must necessarily lag behind the stator rotating field for them to function at all. This is to suggest that within their operational range, synchronous motors are fixed speed motors, whereas we might expect the rotor speed of an induction motor to vary as a function of applied torque. Let us now leave this junction and climb up into the branches of the synchronous motor family and get to work wrecking this place. Within the synchronous motor branch, there are two main types: electrically excited synchronous motors and permanent magnet synchronous motors. Additionally, one might encounter reluctance and hysteresis style synchronous motors, but I'm reluctant, get it, to bring them into the discussion just yet. As one might expect, all members of the three-phase AC synchronous motor family, regardless of construction, make use of a rotating magnetic field in the stator, and inside their operational range, we should expect the rotor to remain synchronized, or to perfectly match the synchronous speed of the rotating stator magnetic field. Given the fixed speed nature of synchronous motors, they make an ideal match for applications that necessitate perfectly timed coordination regardless of applied load. A classic example being a conveyor belt that needs to move at a constant speed, whether it's carrying a box of rice paper origami ballerinas or a crate of sledgehammers. As long as the load within the operational range, a synchronous motor should ideally maintain constant rotational speed. We'll return to discuss the qualification within the operational range in a moment. Both main classes of synchronous motors feature a magnet on the rotor, the principal difference being how that magnet is established. As implied by the title, a permanent magnet synchronous motor really does have a permanent magnet on the rotor and necessitates no additional accessory electrical connections. Whereas an electrically excited synchronous motor, the topic of today's discussion, features a coil of wire on the rotor core called the field between F1 and F2. When the field is energized by an external DC source known as an exciter, It establishes an electromagnet where the strength of the resultant magnetic field is proportional to the current flowing through the coil. More DC current means more magnet, less DC current means less magnet. Once established, the rotor electromagnet locks in with the stator rotating magnetic field and follows it around and around, matching the synchronous speed. For the purposes of this lecture, we're presuming the DC exciter is an external DC voltage source, like an independent battery. However, be aware other types of exciters exist, including those exciters mounted on the rotor. We'll examine three-phase AC rectifiers central to the operation of exciters in greater detail in later exciting lectures. Because an electrically excited synchronous motor necessitates both a three-phase AC source for the stator and another DC source for the rotor, you may hear them referred to as doubly excited synchronous motors. Getting DC electricity from a stationary external exciter to a rotating rotor presents us with a structural challenge not encountered with squirrel cage induction motors, which, if you recall, operate using the principle of induction and do not necessitate an electrical connection to the rotor. Despite the advantages we've yet to discuss, this is perhaps the electrically excited synchronous motor's greatest weakness. How does one send electricity using two wires to something that revolves 360 degrees without twisting the wires into a knot? The device that allows one to do so is known as a slip ring. A slip ring is a means of electrical connection between a rotating and a stationary member. There are several different forms of slip rings, but the most basic configuration takes the form of conductive rings on the rotor shaft, which provide electrical contact to the rotor coil. Stationary conductive brushes held in place by a spring and brush holder ride along the conductive rings, such the field coil on the rotor maintains electrical contact with stationary electrical inputs regardless of orientation. Brushes and slip rings require regular maintenance and will eventually wear out and need to be replaced. This adds an operational expense to electrically excited synchronous motors not encountered with squirrel cage induction motors. This being said, the independently adjustable field on an electrically excited synchronous motor presents distinct advantages. 1. Once the rotor magnetic field locks into the rotating stator magnetic field, electrically excited synchronous motors can be expected to maintain synchronous speed regardless of applied load inside its operational range. This is perhaps the single most recognizable feature of synchronous motors. Inside their operational range, they are constant speed motors. Whether you load them up or underload them, they'll always maintain the constant speed. These devices are not magic, though, and do have practical limits only under which they can perform as advertised and beyond which they catastrophically and violently fail. As load torque increases, the rotor remains in sync with the stator field, however is pulled slightly out of alignment. As load torque further and further increases, the differential between the stator and rotor magnetic field increases and increases. Pull-out torque is the point at which a synchronous motor is so loaded that it pulls out of synchronization. A synchronous motor that loses synchronization is a truly awful experience as line current spikes and the motor's mechanical performance goes to hell. This is not an event you want to prolong, so synchronous motors necessitate out-of-step protection from this undesirable event. We'll examine synchronous motor protection schemes in greater detail in later lectures. Pull-out torque is roughly linearly dependent upon field strength, although there are practical limits to this relationship. At the upper limits of field excitation, we might expect the rotor electromagnet to reach saturation, where pull-out torque starts to flatline. A graph of pull-out torque as a function of field current intensity might look something like this. As field current increases, so does pull-out torque until it reaches saturation, where pull-out torque does not increase despite further increases in field current. As you're no doubt aware, increasing field strength current increases the strength of the magnetic field. This being said, only so many lines of magnetic force can fit into the iron rotor, which concentrates the magnetic lines of force. At a certain saturation point, the sponge is full, and further increases in current don't yield increased magnetism. 2. Additionally, by varying field current, and thus field intensity, one can also observe changes in line current and reactive power consumption for a given load condition. You'll recall squirrel cage induction motors necessitate the constant consumption of positive reactive power necessary to power the rotating magnetic field and drive the process of induction central to their operation. Electrically excited synchronous motors, in contrast, don't operate using induction, but rather have two independent interacting magnetic fields. If the rotor field is weak, the stator needs to draw reactive power, as would a squirrel cage induction motor. If, however, the rotor field increases in strength, the stator doesn't need to consume as much reactive power, thus line current decreases and power factor increases. Additionally, one can overexcite the rotor so much that the stator appears to be capacitive in nature and supplies reactive power. This can be used to power factor correct other loads, as we'll examine in the upcoming synchronous condensers lectures. For today's purposes, keep these graphs in mind. A graph of reactive power as a function of field current looks something like this. At low levels of rotor excitation, the synchronous motor draws positive reactive power and appears as an inductive load where current lags voltage. If field current increases, it draws less reactive power and the phase shift between voltage and current decreases. If field current is further increased, the synchronous motor switches roles and instead supplies negative reactive power and appears as a capacitive load where current leads voltage. This graph also implies an important fact. At a given load condition, field current can be so managed such that the synchronous motor neither draws nor supplies reactive power, and voltage and current are perfectly in phase with one another. This would be an occasion of unity power factor. Speaking of power factor, a graph of power factor as a function of field current looks something like this. At low levels of rotor excitation, the synchronous motor draws positive reactive power and has a low lagging power factor. If field current increases, it draws less reactive power and power factor increases. When field current is adjusted such that the synchronous motor neither draws nor supplies reactive power, power factor peaks out at 1. Finally, as field current is further increased, the synchronous motor starts supplying increasing amounts of negative reactive power such that power factor decreases only in a leading fashion. Given the above described behavior of reactive power and power factor, a graph of line current as a function of field current for a given load condition looks something like this. At low levels of rotor excitation, the synchronous motor draws large amounts of lagging current, accounting for both the real and positive reactive power components. If field current increases, it draws less reactive power, thus current magnitude and phase shift decrease. When field current is adjusted such that the synchronous motor neither draws nor supplies reactive power, current bottoms out and is perfectly in phase with voltage. Finally, as field current is further increased, the synchronous motor starts supplying increasing amounts of negative reactive power, thus current magnitude increases and phase shift increases only in a leading fashion. The graphs of power factor and line current magnitude as a function of field current are essentially inverses of one another, as you might expect. You note I've included a DC overbar in field current, emphasizing field current drawn by the rotor is DC. Similarly, I've included an AC overbar in line current, emphasizing line current drawn by the stator is AC. Do not expect these helpful reminders in a field or lab environment. In ordinary circumstances, I jump right to a practical demonstration and verification of the above properties using a real-world device. However, we're yet to discuss how to start an electrically excited synchronous motor, which is a little more difficult than one might initially suspect. In contrast to squirrel cage induction motors, electrically excited synchronous motors are not self-starting motors and often necessitate more complicated starting circuits than would a similarly related induction motor. One of the principal issues related to starting a synchronous motor is that upon closure of a full voltage starter, the stator rotating magnetic field is instantaneously established at full speed, whereas the rotor in applied load with some level of static inertia may take some time to come up to this speed. The analogy I like to use about starting a synchronous motor is having your buddy invite you to go water skiing. And then he passes you on a dock at 60 miles per hour and then tosses your rope and saying, "Let's go." It's going to rip your balls right out of your sockets if you try to accelerate that fast, and there might be better ways to reach this velocity. An old school method of starting a large synchronous motor was to, believe it or not, use other motors or mechanical means like a gas-powered engine to accelerate and unload a rotor to near synchronous speeds before turning on the exciter. Once locked into the synchronous speed, the motor can be then put to work. Some electrically excited synchronous motors include a small accessory starting motor called a pony motor for this purpose. A more modern method might be to use a variable frequency drive to slowly ramp up excitation frequency on the stator so the rotor is afforded a gentle means of acceleration. You'll often find this method employed with permanent magnet synchronous motors since their rotor field isn't capable of being de-energized nor varied, as would an electrically excited synchronous motor. Finally, smaller electrically excited synchronous motors can often be operated as induction motors during the starting stage to accelerate the rotor to near synchronous speeds before turning on the exciter. This necessitates some modification of the rotor, and that in addition to the field coil reserved for synchronous operation, the rotor needs to include a cage-like structure characteristic of an induction motor for the momentary starting phase. These are called amortisseur or damper windings. Bonus points if you can pronounce amortisseur properly, as I've yet to do so myself. In summary, the desirable constant speed characteristics of synchronous motors come at a price of slightly more complicated, i.e. expensive means of construction, maintenance, starting, and protection. We'll examine electrically excited synchronous motors, exciters, starters, and protection schemes in later lectures. Today's lecture will restrict itself to the mechanical and electrical properties of an electrically excited synchronous motor in steady-state operational conditions. Now that we've got the theory out of the way, let's do a practical demo and call it a day. All right, here's the plan. First, we're going to get the motor rotating, establish a specified field current, and then vary oppositional torque until it reaches pull-out. Along the way, we'll record current, electrical, and mechanical power. Then we'll reset the system, get the motor rotating again, increase field current, and then vary oppositional torque until it again reaches pull-out. Similarly, we'll record current, electrical, and mechanical power. Then we'll do it again and again until we've gained confirmation of the electrically excited synchronous motor properties or break something along the way, whichever comes first. Ultimately, we should be able to generate a bunch of plots showing electrical and mechanical properties as a function of load torque and field strength. Ideally, these real-world plots will closely match the theoretical expectations. For the purposes of this exercise, we're going to use a pretty rugged but admittedly inefficient quarter horsepower rated electrically excited synchronous motor designed to operate with 120 volts line to neutral, 280 volts line to line light industrial three-phase AC in Y configuration. This particular motor has 2 pole pairs per phase, thus at 60 Hz has a synchronous speed of 1800 RPM. Inside its operational range, i.e. under the pull-out torque for a specified field current, we should expect the speed to remain at a constant 1800 RPM. An algebraic manipulation of the mechanical power formula demonstrates this motor rated condition of 1/4 horsepower, 186.5 watts at 1800 RPM should generate roughly 1 Newton meter of torque. This is the condition we'll concentrate most of our analysis on. The first of 4 repetitions shows that at a minimum excitation of 450 milliamperes of DC field current, we start at 0.3 Newton meters of counter torque, which is just enough torque to overcome friction of the dynamometer we'll be using to put this machine through its paces. In this almost unloaded condition, the motor turns at 1800 RPM. As I progressively increase counter torque to 0.5 Newton meters, 0.75 Newton meters, 1 Newton meters, 1.25 Newton meters, and 1.5 Newton meters, the motor remains spinning at a constant 1800 RPM. Inside this operational range, the speed of the electrically excited synchronous motor remains locked with the synchronous speed of the stator, as we might expect. Inside this range, as torque increases, we observe a progressive increase in line current in blue and real electrical power consumption in purple. As we'd expect, for such low levels of field excitation, the synchronous motor consumes positive reactive power in pink and current lags voltage as if it was an inductive load. Interestingly enough, reactive power remains relatively constant throughout the operational range, only increasing at the very end. Things go bad at 1.7 Newton meters. At such low levels of field current, the motor quickly reaches pull-out torque and loses synchronization. Rotor speed dramatically drops, line current spikes, and the motor starts making sounds like it's being pulled through a knot hole backwards. Shut her down. No good can come of this. Let's do a second repetition of this with increased field current. When I step up excitation to 540 milliamperes, we again start at 0.3 Newton meters of counter torque. In this almost unloaded condition, the motor still turns at 1800 RPM. As I progressively increase counter torque to 0.5 Newton meters, 0.75 Newton meters, 1 Newton meters, 1.25 Newton meters, and 1.75 Newton meters, the motor remains spinning at a constant 1800 RPM. Inside this operational range, the speed of the motor remains locked with the synchronous speed of the stator, as we might expect. You note with increased field current, we exceeded the previous pull-out torque value. As previously, inside this range, as torque increases, we observe a progressive increase in line current in blue and real electrical power consumption in purple. Something interesting is happening with reactive power with this level of increased field current. You'll note the synchronous motor still consumes positive reactive power in pink, however, not as much as previously. As before, reactive power remains relatively constant throughout the operational range, only increasing at the very end. With this level of increased field current, things start to go bad at 2 Newton meters. As previously, the motor loses synchronization and line current spikes. Shut her down. All right, third rep. Let's do this again with increased field current. When I step up excitation current to 630 milliamperes DC, we again start at 0.3 Newton meters of counter torque. In this almost unloaded condition, the motor turns at 1800 RPM. As I progressively increase counter torque to 0.5 Newton meters, 0.75, 1, 1.25, 1.5, 1.75, and 2 Newton meters, the motor remains spinning at a constant 1800 RPM. Inside this operational range, the rotor remains locked with the synchronous speed of the stator, as we might expect. You note with increased field current, we exceeded the previous pull-out torque value. As previously, inside this range, as torque increases, we observe a progressive increase in line current in blue and real electrical power consumption in purple. Something cool is happening to the reactive power with this level of increased field current. You'll note for a majority of this operational range, not only has reactive power consumption decreased, it's actually gone negative, i.e. supplying capacitive reactive power, only crossing into the positive inductive realm at the very end. This level of increased field current, things start to go bad at 2.25 Newton meters. As previously, the motor loses synchronization and line current spikes. Shut her down. All right, last rep. Let's do this again with maximum field current. When a step-up excitation is 720 milliamperes DC, we again start at 0.3 Newton meters of counter torque. In this almost unloaded condition, the motor turns at 1800 RPM. As I progressively increase counter torque to 0.5 Newton meters, 0.75, 1, 1.25, 1.5, 1.75, 2, and 2.25 Newton meters, the motor remains spinning at a constant 1800 RPM. Inside this operational range, the speed of the rotor remains locked with the synchronous speed of the stator, as we might expect. You note with increased field current, we exceeded all previous pull-out torque values. This is as tough as this particular motor can get. As previously, inside this range, as torque increases, we observe a progressive increase in line current in blue and real electrical power consumption in purple. As previously, with this level of increased field current, for a majority of the operational range, reactive power has gone negative or capacitive, only crossing into the positive or inductive realm at the very end. With field current pegging the limit, things start to go bad at 2.5 Newton meters. As previously, the motor loses synchronization and line current spikes. Shut her down. Let's review what we just witnessed. First, pull-out torque increased roughly linearly as we increased field current. At 450 milliamperes, it lost synchronization at 1.75 Newton meters. At 540 milliamperes, it lost synchronization at 2 Newton meters. At 630 milliamperes, it lost synchronization at 2.25 Newton meters. And finally, at 720 milliamperes, it lost synchronization at 2.5 Newton meters. Every time it lost synchronization, speed and torque dropped, line current spiked, and the motor started bucking and snorting like a bronco choking on a stripper's scarf. This is obviously something to be avoided in regular operation and necessitates sophisticated out-of-step protection schemes we'll examine in greater detail in later lectures. If we kept on and on increasing field current beyond the manufacturer's recommendations to 900 milliamperes or 1 amp or even 1.2 amps DC, we might expect only marginal increases in pull-out torque, with it eventually leveling out and flatlining due to saturation. Long story short, increased field current results in a stronger motor with an increased operational range. This being said, there are practical limits. Let's now discuss what we observe regarding line current, real, and reactive power. For all levels of field current excitation, we observe roughly linear increase in current and real power for increased levels of counter torque. Makes sense. More counter torque means more mechanical power, thus the motor draws more current and consumes more real electrical power. Something cool happens with reactive power at different levels of field current. At low levels of rotor excitation, the motor draws positive inductive reactive power. As we increase field current, the motor draws less and less positive inductive reactive power. As we continue to increase field current, at a certain point, the nature of reactive power flip-flops and the motor starts supplying negative or capacitive reactive power. Further increases push it well into negative territory. This confirms the theoretical plot of reactive power as a function of field current. At low levels of field excitation, the motor consumes positive reactive power. At high levels of field excitation, the motor supplies negative reactive power. This also implies there's a balance point in there that we skipped over. The motor should neither draw nor supply reactive power, and not only will current be in phase with voltage, but also achieve a minimum magnitude. This necessitates further inspection. It's kind of hard to see the details on these larger plots with all this data, so let's zoom into one condition, the rated condition of 1 Newton meter, and show in real time how variations in field current affect line current magnitude and phase shift. Here I'm plotting voltage across and current through winding 1 in black on top, voltage across and current through winding 2 in red in the middle, and voltage across and current through winding 3 in blue on bottom. At a minimum excitation of 450 milliamperes, when I load the motor up to 1 newton meter of counter torque, i.e. the rated condition, current is clearly lagging voltage, as a magnitude of roughly 700 milliamperes. Yes, current's a little distorted, but if you squint your eyes just right, you can see where the sine wave is. Remaining in the rated condition of 1 newton meter at 1800 RPM, when I increase excitation current to 540 milliamperes, the phase shift between current and voltage decreases, and line current magnitude drops to roughly 646 milliamperes. Similarly, remaining in the rated condition of 1 newton meter at 1800 RPM, when I continue to increase excitation current to 630 milliamperes, the phase shift between current and voltage continues to decrease, momentarily appears in phase, and starts to lead with a magnitude of roughly 638 milliamperes. We'll come back to examine the in-phase condition in a moment. Finally, remaining in the rated condition of 1 newton meter at 1800 RPM, when I max out excitation current at 720 milliamperes, the phase shift between voltage and current continues to increase in a leading fashion, and magnitude increases to roughly 663 milliamperes. For those that missed it, let me describe what happened. As we progressively increase excitation current, not only did the lagging phase shift between voltage and line current decrease, become in phase, and start increasing in a leading fashion, current magnitude decreased, reached some minimum value, and then started increasing. This confirms our earlier theoretical expectation that there's some value of field current at a given load condition, in this case the rated condition of 1 newton meter at 1800 RPM, that the motor neither draws nor supplies reactive power, voltage and current are in phase with one another, a unity power factor, and current reaches some minimum value. Let's see if we can find that sweet spot. Let's just concentrate on winding 1 only and start from the beginning. Voltage across and current through winding 1 appears in black and dark gray. Power appears in, magenta. I don't know what color that is. At 450 milliamperes of excitation current, line current clearly lags voltage. There are brief exchanges of reactive power above and below the horizontal axis. When I increase excitation current to 540 milliamperes, the phase shift decreases and the exchanges of reactive power above and below the horizontal axis decrease in magnitude. When I increase excitation current to 630 milliamperes, phase shift continues to decrease, becomes in phase, and starts to lead. Went a little too far. I'm going to dial it back to right about there. When I dial the field current back down to 600-ish milliamperes, looks like voltage and current are perfectly in phase with one another, and current reaches a minimum value of roughly 620-ish milliamperes. Long story short, by balancing field current for a given load condition, an electrically excited synchronous motor can power factor correct itself. Pretty neat, huh? We'll examine how an unloaded synchronous motor, often referred to as a synchronous condenser, can power factor correct other loads in an upcoming lecture. Until then, that's all I got for you today. In conclusion, this lecture examined the construction and theory of operation of electrically excited synchronous motors, as well as examined their mechanical and electrical properties while in operation. Additionally, we examined how the field strength influences pull-out torque and electrical performance at various load conditions. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.